Hello everyone. Today we will be connecting what we have learned earlier in the year to how we have been studying the behavior of a function using calculus. Our goal is going to be sketching a function by hand and understanding the behavior. While we're going to be doing most of the work by hand, you may use your calculator to guide you as an aid. Our basic guidelines for analyzing the graph of a function is to always identify the domain and the range just to get a sense of what may be going on in the function. You're going to find your x and y intercepts, any vertical asymptotes, if any. Okay, remember, there are specific cases where we have them and when we don't. And we're not going to worry about the symmetry of the graph at this point in time. We want to find any critical points and intervals where the function is increasing and decreasing. We're going to use the first derivative. We want to determine any local maximum or minimum points. Local is just another word for relative. We're going to use the first derivative, and then we're going to determine concavity and points of inflection, and for that we're going to use the second derivative. Lastly, we're going to sketch the curve. Okay, we're going to graph these two curves together in class today. What I want you to do is get yourself a nice clean sheet of paper. While you're doing that, I'm just going to mention a few things. Before we move on with this lesson, I want to remind you, we're just using these methods to help us understand how the information we get using calculus connects to the function itself. We're going to use our calculator if we need to visualize the curve. That's okay. There will be times in calculus when we don't want to graph the function, but we still need to obtain information about a function. And graphing now helps us see that the values we get are justified. Okay, so we're going to begin with our first curve. And that's going to be f of x equals x cubed plus 3x squared minus 9x plus 5. Okay. Now remember, we're going to find the domain and the range. Well, when I look at this, my domain, it's a polynomial. My domain is all reals. My range is all reals. So basically what that tells me is I don't have any real issues here. Okay. My next step is going to be to find the x-intercepts and the y-intercepts. How do we find the x-intercepts? Well, we find the x-intercepts by setting the function equal to 0. And in this case, it's not going to be so easy to find the x-intercepts because if you notice, I can't factor this. So when we can't factor something, we have to use synthetic division. If you don't remember synthetic division, that's okay, because I'm going to show you later. We can just kind of cheat at this point. With synthetic division, we have to have an x-intercept to start with. My hint here is to always start with 1. Use that as your guess. More often than not, it's going to work. Or I get -5, -5, 0. So basically what we did was we broke this original function into 2 factors. And now I can easily factor this trinomial and clearly see my zeros. Said the word 0, I wrote the word 0. I can clearly see my zeros from the factors. Now remember, when the factor occurs more than once, that just means it's going to bounce. So I really only have to worry about that. My y-intercepts. The y-intercepts we get by plugging 0 into the function. And my y-intercept here is going to be when y equals 5. Okay, so I have my x-intercepts and my y-intercepts. The next thing we're going to do is we're going to talk about finding the critical points and identifying the intervals where the function is increasing and decreasing. And we're also going to identify any relative maximum or minimum values. So to get the critical values, I have to go back up to my function and take the derivative. Since it's a polynomial, it's real easy. And now I'm going to set this function equal to 0. Now, I expect you to be able to do this math on your own. When we go to find our zeros, we factor. I can just disregard that 3, because if I divide it over, I'll get this. And the zeros of the derivative are, I get x plus 3 and x minus 1. So negative 3 and 1 are going to be critical values for this function. And what do we do with these critical values to see where the function is increasing and decreasing? We put them on a number line. This is my f prime number line, negative 3 and 1. Now I'm going to give you a few seconds to kind of work through your signs on your number line. Okay, so I'm going to let you do this work on your own. If I take negative 4, so I have my function is increasing, decreasing, and increasing. Now, from here, we also want to find any relative maxes or mins. So I know that when I go from a positive to a negative, negative 3 is going to be a maximum value on my curve. How do I get the y value? I get the y value by plugging negative 3 into my original function. I will also give you a second to work that out on your own. And you should get negative 32 as a maximum value. Next, we're going to want to find the second derivative. Now, I'm going to leave just a little bit of room here. Okay, for my second derivative, I'm going to do the work down here. So f double, I'm going to move it down just a little bit, because I want to put my number lines next to each other. And my second derivative becomes 6x plus 6. When I set that equal to 0, I get that x equals negative 1. Oops, I forgot to do the minimum value. My minimum is going to occur when x equals 1. So the point on the curve is going to be whatever value I get when I plug 1 into the original function. And you could take a second and do that on your own. And you should get 0. Sorry about that, guys. Moving back down to the second derivative. Notice how I'm putting my number lines kind of next to each other. I'm doing that on purpose. So my negative 1, if I was going to kind of line these up, it's not great, but it should be about there. And if I test each interval now, remember we're testing in the second derivative. If I plug a number less than negative 1 in, let's say negative 2, I'm going to have a negative number, negative value, which means my curve is concave down. And then if I plug a number bigger than 1, negative 1, I'm going to get a positive interval, which means my curve is concave up. And since my curve changes concavity, this means that at x equals negative 1, I'm going to have a point of inflection. Now to find that point of inflection, we're going to plug negative 1, once again, into our original function, and we should get 16. So my point of inflection is at negative 1, 16. All right. So now I have all of my basic information, and I want to kind of sketch this thing. Now here's where this is kind of hard to understand. But basically what's happening here is my curve is from negative infinity to negative 3, it's increasing and concave down. From -3 to -1, it's decreasing and concave down. At -1, it's going to be decreasing and concave up. So see how the shape of the curve is going to change. At 1, I'm going to have my minimum value, and then my curve is going to be increasing and concave up for the remainder of the domain. Let's just here's where I said you can bring your calculator into it to see what's going on. This is the curve, x cubed plus 3x squared minus 9x plus 5. This is the graph of the function. Notice, okay, we can't see the whole thing, but it's sort of following the pattern that we just saw. So we're going to kind of take all of this information and put it together and make ourselves a little picture now. What were some of the important things? And again, this is a sketch. It's not going to be perfect. My x-intercept was at -5. Another x-intercept was at 1. My y-intercept was at 0, 5. I'm going to kind of not go too far. So that's -5, 0, 0, 5, 1, 0. Now remember, our curve is going to kind of go all the way up, and it's going to hit a maximum at -3, and that maximum value was 32. Our curve is going to be concave down. And then we have a point of inflection at -1, so I'm going to decrease, and my point of inflection was -116. Again, kind of hard to do this by hand, but you do have your calculator to help you see the shapes. My graph is decreasing and concave down. Then my graph changes, and it becomes the point -116. That's my point of inflection. Now my graph is going to go through, be concave up, go through the y-intercept and hit its minimum value. Notice it's concave up, and then it's going to continue on for the remainder of the domain. So there's your finished product. I know it's a little bit of a challenge, but check out your calculator while you're graphing it, and you should be okay. Let's move on to the second example. My second example is a rational function. So in my head, when I'm thinking about the domain and the range, I have to kind of realize there's going to be an issue here. Where is this function undefined? Well, it's going to be undefined. X can't equal -1/2. Okay, so I can't plug the value -1/2 into this function. And clearly, you guys hopefully can see that this is going to be an asymptote in our curve, but we'll talk about that in just a minute. Our range, I'm going to hold off on our range for a minute because it is a little bit confusing to think about. Just remember, there's issues here. Okay, we're going to have issues with this curve. So now we want to find the x-intercepts and the y-intercept. Well, the x-intercept is when the function is equal to 0. And since this is a rational function, it's just going to be where the numerator is equal to 0. So I'm going to have an x-intercept at x equals 2/3. The y-intercept is what I get when I plug in 0. So my y-intercept is going to be at -2. Now let's see what happens with our increasing and decreasing and our maxes and mins. Okay, so for that we're going to look at the first derivative. So if my original function is here, I'm going to have to use the quotient rule. Now I'm going to give you guys a few minutes to work out the quotient rule on your own. You could check my notes here. If you want to pause the video, you can. But ultimately, after you do all your work, you should get the first derivative to be 7 over 2x plus 1 squared. Now, what are we going to do with that information? We're going to put it on our number. Well, first we have to find the critical values. So, since it's a rational function, derivative equal to 0, derivative undefined. Where is this derivative equal to 0? When the numerator equal to 0, and there's no critical values of that nature. Let's look where this function is undefined. 2x plus 1 squared equal to 0. Square root both sides. So now this function is undefined. The derivative is undefined at x equals negative 1/2. But remember, we excluded that value from the domain, and based on the nature of this function, we can't simplify it. So this pretty much will be probably an asymptote. If you want to double check it, evaluate the limit as x approaches negative 1/2. If you want to see if this is a vertical asymptote, evaluate this limit, and you get a 0 in the denominator. Since we can't factor this and try again, we realize the limit does not exist, which makes this an asymptote. That's going to be helpful when we're graphing our function. Okay. So now we have this number, negative 1/2. Technically, it's not a critical value. But remember, it's important when we're graphing our function. So we're going to make our number line, put negative 1/2 on. I usually use a squiggly because I want to remember there's something going on here. Most likely an asymptote, but we're not sure at this point. When I have a number less than negative 1/2, if I plug it into the derivative, notice my derivative is going to be positive in the numerator in either interval. And no matter what number I get here, if I square it, this is also going to be positive. So this function is increasing over the entire domain. That's what that means. However, something's going on. So now let's find the second derivative and see what information that gives us. F double prime of x equal to 0. Okay. How do I get the second derivative? I'm going to start with the first derivative and take the derivative of that function. Once again, I'm going to give you a few minutes to work this out on your own. I'll put the answer up here, but I want you taking the time to work it out. So now that we know our second derivative, negative 28 over 2x plus 1 cubed, we have to go through the same steps. It's a rational function, f double prime equal to 0, f double prime undefined. Well, this function is equal to 0 when the numerator is equal to 0, and clearly that doesn't happen. This function is undefined. Take the cube root of each side. So the second derivative is undefined at x equals negative 1/2. Now remember, since it's undefined, it means, and we can't use negative 1/2 in the function. It's one of these weird values. We put it on the number line anyway. So if I go up here on make a second derivative number line, put negative 1/2 on there. If I'm going to test in my intervals, let's say I take a number less than negative 1/2. When I plug it into the second derivative, the numerator will always have a negative value. The denominator now, it's going to depend on what's going on. So I have a negative 2. I'm going to have a negative number and cube it. The second derivative will be positive in this interval, which means your function is concave up. if I go over here, bigger than -1, -1/2, and I plug a number in, let's say we take 0. So I have a negative in the numerator, and I have a positive in the denominator. The second derivative value is negative, so my function is concave down. So basically, what's going on in this curve, now remember, I have no maxes or mins, okay, and even though my sign changes, I'm changing concavity, but this is not a point, because I cannot plug -1/2 into the original function. I won't get an answer. So basically, the curve, what's going on is increasing in concave up. My curve should kind of be going like that. Increasing and concave down. So my curve should be kind of looking like that. Now this is real hard to visualize, and I did forget one last thing. We're dealing with a rational function, so our rational function is going to have some sort of horizontal asymptote, right? We have to figure that out right now. How do we find a horizontal asymptote? Well, if you remember correctly, we look at the original function, okay, and determine end behavior. What's the end behavior of this? It's a ratio of the coefficients. Okay. So if we put this information together, now you have your sheet in front of you. So use this as a guide. I have an x-intercept at 2/3. I have a y-intercept at -2. I have a horizontal asymptote, right, where the function is undefined, at -1/2. And I have a horizontal asymptote at 3/2. Now, we said we're going to connect our curve, and remember, our curve is increasing and concave down. And I'm not quite sure what to do on this side, so when I'm not quite sure, I know it's going to be increasing and concave up. I think if I'm increasing and concave up, I sort of have to go like that. But let's use our calculator and double check it. So I'm going to wipe out what's here. Take a quick look at this picture and see if it matches what we came up with. And it does. Okay. Now again, don't get too scared. Practice what you can, and I will be seeing you soon.